Alright, so we're going to walk through this resistor problem with a way that I feel like makes it a little bit easier to understand what we're trying to find. That way we can all kind of understand it a little bit better. So here we have our circuit, which has 6 different resistors on it. And what I've done with each one is showcase that we're finding, or we're given the resistance of each one in ohms, and we're trying to find the voltage drop for each one, as well as the current going through each one. So step 1 is to condense the entire thing into one resistor. That way we can find the current of the entire circuit. So taking this top chunk, when they're in series, we just add it together, so we get 9 ohms. The bottom chunk, we have 2 that are parallel, and then 2 ohms down the line. And in order to find this parallel sequence, we multiply on the numerator and then divide by them added together. So we get 7/8 ohms, and the 7/8 plus 2 gets us to 23/8 ohms. So now, after reducing, we have 9 ohms on the top portion and 23/8 ohms on the bottom portion. And doing the same concept that we did here, we can do that again with these two. Multiply on top, add on the bottom, get 207/95. Now, if we went back and expanded, we have our 3 ohms at the beginning and our 207/95 ohms here that we just figured out. And when we add them together, because they're in series, again, when they're in series, we can just add them together. We get 492/95. And just for the sake of better numbers, we can approximate it to about 5 ohms. So now that we know the equivalent resistance of the entire circuit, we can use that to start actually solving and filling in some of our gaps. So for the first resistor, the current going through the circuit is the same going through this first resistor. And so using Ohm's law, we have the current is equal to the voltage divided by the equivalent resistance. So 15 volts over 5 volts, over 5 ohms is 3 amps of current. And so if we go back up here, we can put in 3 amps of current there. And so we still need to find the voltage drop. And again, using Ohm's law, voltage equals current times resistance, which the 3 amps that we just found times the 3 ohms of that resistor gets us 9 volts. So now we've completed that first section. Now we'll go ahead and start doing the top portion here. So we know that there are 6 volts for this section because 9 volts have been consumed from that first resistor. Therefore, there's only 6 volts left. And when resistors are in parallel, they both have the same voltage going through them. So on the top portion, like we were just saying, to find the current, which the current is the same when resistors are in series, we have 6 volts over 9 ohms, so 2/3 amps. So we come back up here, and again, like I just said, when resistors are in series, so one after the other, then the current is going to remain the same. So we found 2/3 amps. It's going to be the same going through both. Voltage, though, is going to be different. So we have to go back and calculate that as well. So if we know what our current is and we know what our resistance is for each of these two, we can find the voltage for both. So the voltage of this one on the left here, current times resistance, 2/3 amps times 4 ohms gets us 8/3 volts. And then since we do know that it's 6 volts going through it, you can technically use deduction to figure out the remaining voltage for the other portion. But you could also calculate in this instance where you get 2/3 amps times 5 ohms, you get 10/3. And one way that we can check to make sure we're on the right track is we can add these two and we get 6. So 8/3 plus 10/3 equals 18/3 is equal to 6 volts. So we go back up here, 8/3 volts, 10/3 volts. So now we've solved pretty much half of the entire thing. And now we go to the bottom portion. So again, the voltage overall is 6 volts. And the current has to be the remainder to reach 3 amps. And since the top portion we calculated to be 2/3 amps, we can use deduction to figure out that the bottom portion must have 7/3 amps of current. So I have this little analogy here where the flow of a river, where if a flow of a river is going through here, it's going to split into two, but then it's going to join back into one current. Hence, this current going through here is the same current going through here, which is 7/3. And so if we know that the current there is 7/3 amps, we can use that times the resistance to figure out the voltage drop from this resistor. And we get 14/3 volts. So we go back up. We've solved for that one. So now for this portion, we know that the voltage, when in series, voltage is split up. And so the voltage needs to add up to 6 volts. And in order to get to 6 volts from 14/3, we have to have 4/3 volts. Therefore, 4/3 volts goes into this portion. And then again, like we were saying before, when two resistors are parallel to each other, they have the same voltage. So both this top and bottom resistor have 4/3 volts. So we go back up. Boom. And now all we have left to do is figure out the current. And again, thinking about our little current situation where it's the same current here joining up as one. These two currents are going to equal 7/3 amps of current. And so for this top one, where the resistance is 1 ohm, it's volts over resistance. So 4/3 over 1 ohm equals 4/3 amps. And then the other one, again, you could either deduce that since it needs to equal 7/3, the other one is 1 amp, which gives us that. Essentially solving the entire problem, where the top here, 4/3 amp, and the bottom portion is 1 amp. And therefore, you can check and see, double check your work, 9 volts, and then 6 volts here, and it's the same exact on the bottom because when they join back up, it's still 6 again. So that's 15 volts dropped, and then the current, 3 amps, you have your 2/3 amps, plus the 7/3 amp gets 3 amps. And that's it. You've already solved the whole thing.